Okay, so first set of models and acids and bases. The beginning of this is going to seem like review from last year. Then it's going to quickly develop into new stuff. So, Arrhenius definition. Acids produce the hydrogen ions in solution, and then, of course, for the bases are going to produce the hydroxide ions in solution. So this is the very basic definitions that we tend to follow, but when we get to AP, we step it up. Definitely going to go way beyond that initial concept of just producing hydroxide or hydrogen ions in water or solution, but the solution is usually going to be water. Now looking at the Bronsted-Lowry definition, which is what we're going to be concentrating more on here, is the idea that acids are proton donors or proton acceptors. And when I refer to the word proton, I'm talking about an H+, because essentially if hydrogen loses its one electron, it is essentially just a proton. So we'll be referring to H+ as being the proton. And up here we're going to be looking at water as acting as the acids or the base. And when a compound can act as an acid or a base, it's considered to be amphoteric. And water's not the only one that's amphoteric, but you're going to be seeing that quite a lot in these examples. So I just wanted to show that because according to this definition, you have to be able to accept H+, or you have to be able to donate an H+, and water has the ability to do both. But what we probably didn't cover in detail last year in Chem 1 was this concept right here. When the H will donate to the water here, it forms something called hydronium. And technically, the H+'s don't just sit around and float around in the water or in between the waters. They actually attach themselves to the waters and form the hydronium ion. And so when we're saying it's producing H+ ions in water, it's really producing a bunch of hydronium in the water. And then, as you see here, they have the double arrow, and this is going to be establishing an equilibrium position as to how much of the acid is going to break apart and ionize. So we're going to be looking at a whole lot of things here. There's definitely a lot of equilibrium concepts that run with acids and bases here. So, another look at hydronium here. Basically, this is the ball and stick kind of model. Here, plus the proton, gives you this structure with the 3. Here's the Lewis structure. You can see, because it is a charged particle, it ends up with the brackets around it. Here's more of the 3-dimensional Lewis dot structure, electron pair geometry, showing you that it's basically giving you kind of a pyramidal look, because it has its lone pair up top, then 3 bonded things at the bottom, so it's giving you a pyramidal shape. It's a tetrahedral pair geometry, but a pyramidal shape, as you see over here, as that's what I was thinking, without the lone pair on the top causing the tetrahedral part. It is just with the actual individual atoms, it's going to be the pyramidal shape. So that's a kind of a look here as to that idea of hydronium. So when we're really talking about H+'s in solution here, we're really looking at this new concept of that the H attaches to water and forms hydronium. Okay, so acids in water. We're going to go back over this in a little bit more detail, but as you saw in that particular one, we had stuff over here on the product side. The acid and the base are always on the reactant side of the double arrow, and then you have your conjugates. The conjugate base is what remains after the acid molecule, after the proton is lost. And then, so it's basically the acid with the missing H. That's how I like to look at it. Follow the H. Follow where the H goes, and you can figure out who's going to be the conjugate acid and who's going to be the conjugate base on which species is going to do that on the right-hand side here. Conjugate acid is formed, when the proton is transferred to the base, so it's basically going to be the base now having an H attached to it. So we're going to look at this in more detail, but you're going to see these as we go through them, and we're going to label them. So I wanted to go back over those words, those vocab words one more time before we continued on. Okay, so now we're going to look at the Arrhenius acid reaction with hydrochloric here. So what do you think is going to happen here? It's going to we're just writing out the reaction. So we would just break it apart, put it AQ, right? Just like so. Producing the hydrogen ions in solution. We put the AQs next to it to indicate solution. We're basically not going to be drawing them a whole lot like this unit. And if I wanted to show the same thing for like the base version here, you know, you would take like your lithium hydroxide, which would be a strong base, and we would actually would only have an arrow going this direction, right? Because it's pretty much going to completion, and you get your Li plus and your hydroxide over here. So this would be an example of, you know, the base version. But remember, the base version of the Arrhenius definition is very narrow because you have to have some kind of hydroxide being made in the solution for it to be considered part of that definition. So in this case, the lithium hydroxide works because it's going to break apart. It's one of the strong ones. The alkali metals, remember, are the strong bases. Calcium, strontium, and barium are considered strong, but they're really in that slightly soluble category that we just found out in KSP. But if we want to do the Bronsted-Lowry acid reaction, now we're going to be looking at it in terms of the acid is reacting with the water. So we have an acid plus a base. We're going to be having the acid donating the H to the base. I like to draw arrows. So over here, we're going to end up with what? H3, the hydronium, and the Cl minus. Good. And if we were to label these, this is going to be the conjugate what? With conjugate acid, good, because it was the base, but now it has that H attached to it. And this one over here is going to be the conjugate base. Good. Okay? So we're going to be looking at and drawing ours mostly from this kind of standpoint from now on, looking at it in this perspective. All right, let's look at ammonia as both Arrhenius and Bronsted-Lowry base. This one's a little bit in the category of, well, ammonia can't in and of itself make hydroxide, right? Because it doesn't have any O's in its chemical formula. But, you know, it is a little bit of, you know, gray area, because you can say, what can the ammonia do here? Water, right? Yes, if we go this way, this one donates, right? So this is now the acid. The ammonia is the base. We end up with what over here on the side? NH4 plus, okay, and OH minus. So technically, when ammonia is dumped into water, it actually does produce hydroxide ions. Those hydroxide ions are being formed from the water molecule, but it is still forming them. So it kind of, you know, it's a little murky, but can fit that definition, okay, because you do have some hydroxide being produced. But the Bronsted-Lowry base definition is definitely better, looking at it from accepting and donating the proton. Over here, which one's the conjugate acid? NH4 plus is your conjugate acid, and your OH or hydroxide is going to be the conjugate base. And you need to get used to recognizing those immediately, because we need the conjugate acid-base pairs. We'll be talking about the pairs later, but this is basically a pair. The base goes with this conjugate acid, and then we have our acid goes with its conjugate base. So those are going to be the conjugate pairs. All right, so far so good? So I did want to show you one where, this one isn't really in the notes, but I did want to show you one where we're looking at Bronsted-Lowry without the hydroxide at all involved. So as you see here, phosphate is reacting with nitric acid, and we're going to get some nitrate and some hydrogen phosphate out of it. But do you see hydroxide at all up here? No hydroxide. So basically we have acid donating to the base, okay, and no hydroxide involved, fitting the Bronsted-Lowry definition, showing the donor, ending up with your conjugates over here on this side. But you might see reactions like that as well, where you don't see any hydroxide at all, and it still is part of the definition. Now, revisiting the idea of the strong versus the weak concept. We went over strong acid-base chemistry a lot in Unit 1, but we didn't really go into the weak acid-base equilibrium ionization stuff in Unit 1. Strong is supposed to completely ionize or completely dissociate. So when I say ionize, they're separating into their ions and forming ions. So that's what that word, ionization, equilibrium, lies far to the right. It's basically breaking apart, completely dissociating, forming the ions. And in that process, the conjugate is going to end up being very weak. Very, very weak. In the weak acid situation, it's kind of the opposite. The ionization equilibrium lies far to the left. Very little of it ionizes or dissociates. That's when we said partial dissociation. Partial is even kind of a strong word because some of them are so weak that they hardly ionize. They have really small values, like you saw in the KSP dissolving process, where those KSP values were really small and they were basically very insoluble. Well, it's the same idea here. This acid is hardly going to break apart, hardly going to make ions, and the equilibrium position will lie basically on the left-hand side. The weaker the acid, the weaker the acid, the stronger the conjugate base, and it will, help keep that position in place. Okay? So we have our two basic definitions here. One that's completely dissociating, one that's hardly dissociating. Well, actually, it's based off of their Ka value, so you'll see it's a range, it's a gradient, just like KSP, where some, will ionize better than others. Yes? A weak conjugate base would be like chloride. We have HCl, right? Or when it reacts with the water, you end up with your hydronium over here and your chloride, right? But this one really shouldn't be drawn with a double arrow like I did, because basically it goes to completion. There is like that much of that. So it basically all goes to completion. There's hardly anything reversing there. Okay? So any of your strongs, your 7 strongs, are going to be just like this. So their conjugate bases are all going to be weak, very weak, on the 7 strong acids that we know of. And you have to go back, and if you don't remember them, you're going to have to rememorize those 7 strong. So you can easily identify anything that's weak. If you know your 7 strong, everything else is weak, you'll be able to identify them immediately. Okay? So here is just a nice picture, and this one's in your notes to show you. This would be like the hydrochloric example that we just talked about. We have HCl. You're going to get the H and the Cl's over here. But this one would be more like, say acetic acid. Acetic acid, everybody know the common name for that? Vinegar, there you go. So basically, as you would see, most of them are staying together. Only very few of them actually separated into the ions. Okay, the ones I circled in red are the ones that actually separated apart and are in the ion form. So as you see, this part of the graph very short. Most of the acid will stay together. And that's what's kind of showing you in the graph there. Whereas in the graph to the left with the strong acid, everything breaks apart. Everything dissociates, everything becomes an ion or ionizes. Okay? Good with that? So our 7 strong, let's remember them. Let's write them down. The 3 in the halogen category, skipping fluorine. So hydrofluoric is not in that list, but hydrochloric, hydrobromic, hydroiodic. Then you have your ones that are in like the chlorate category, right? This is how I group them, the chlorate category. You've got perchloric and chloric. And then you have your polyatomic category, which is the sulfuric and the nitric. Now, we're going to talk about sulfuric too, because sulfuric technically is only strong on the first H. So we're going to look at some examples like that. The second H is very weak, because it's a diprotic one, right? It has the 2 H's here. So that's a diprotic acid. Really, only the first one coming off is actually a complete dissociation and very strong. So anything not on this list, you should immediately recognize as being weak and do weak acid equilibrium type problems with. So when you see, oh, it's a weak one, I got to do it this way. Okay? So you got to be able to recognize, if you know all 7 of these, you'll know everything else that we will put in a problem will be considered weak. Some other ones that are common, though, for the weak side of things that, you know, want to make sure that you know these ones. The HSO4, which is the hydrogen sulfate, that's after you take off the first H off of the sulfuric. That conjugate is really a weak acid. Pulling off that second H is not going to happen very often. It doesn't ionize too much. Hydrofluoric is the one halogen basically that's weak, so you got to remember that one. And then the one I just went over before, vinegar acetic acid, that one's a very typical weak acid you'll see quite frequently. Okay? Alright, so let's look at the sulfuric example. We have our sulfuric being diprotic, has 2 protons in it. The first proton, like I said, is considered to be strong. So that first reaction, that one is going to go to completion, pulling it off. The second one, though, is very weak. Okay, so that's why you'll notice it has the double arrow, because it's showing you that it's going to have an equilibrium position. It's going to have a Ka value that's small. We're going to get into the Ks again, but basically Ka is just an equilibrium constant for the ionization equilibrium position of acids. So this one, the position's going to lie far over here to the left. Here, this one has the arrow going that way. Because it goes to completion, it pretty much everything dissociates. That first one is very strong. And, you know, our Ka for this one is going to be large because it's pushing towards the products. If you remember our generalized idea of K is the products over the reactants ratio raised to the powers and all that other stuff. But generally, if we are forming only products, our Ka is going to be very, very large. If we mainly only have reactants, which would be in this case, the K is going to be very small. So it's back to that equilibrium idea again, but we're now just taking that concept and applying it to the weak acid and weak bases. Water, as we said before, is amphoteric. So here, behaves like an acid when it's reacting with ammonia. Showing this reaction here, we already did this at the beginning, but as you see, it's donating the nice graphic, okay, giving you the hydroxide and the ammonium. When it behaves like the base, here, this example, sulfuric donating the 1, creating hydrogen sulfate, or it's also called bisulfate, okay, and this case, yes.
Does it matter if the base is strong or weak? Because like you know like strong acids, but if there's a weak, like there are weak bases.
Yes, there are weak bases. Our strong bases are all the alkali metals with hydroxide. So all those hydroxides are strong. And the book, and people still classify calcium, strontium, barium hydroxides as all being strong as well. But, and they do produce pretty high pHs. But as you saw in the KSP lab, that not all of it's soluble. It has a KSP somewhere like in the 10 to the minus 6. So it's really in that slightly soluble category. So it doesn't completely dissociate, but it does create higher pHs, so I'm assuming that's why they group it into the stronger category. But no, strontium, barium, and calcium end up with, you know, KSPs, so that are a little bit smaller than what you would consider strong. So they kind of fall in that slightly soluble in terms of strength category, or what I like to think of. But definitely alkalis, they all completely dissociate from their hydroxides. But yeah, when you're looking at the weak bases for these particular problems, they're going to have like NH compounds in them, like ammonias, amines, and things like that. You're going to see those frequently in the weak base category. You'll see them as they pop up, and it will identify it for you in the problem. This is a weak base with a KB of, and it will tell you, yes. Or this is a base that has a KB of, so you can recognize that it's weak, yeah. Self-ionization of water. We're on to that already, huh? So here is our reaction. It's basically water reacting with itself. And it does this all the time. So it reacts with itself, it creates hydronium, it creates hydroxide, but guess what? Just as fast as it does that, it goes back and transfers it back and makes the 2 waters again. So it's just going back and forth, back and forth. It's a pretty dynamic process. Self-ionization of water. But it is constantly happening in a glass of water or a bottle of water. So 2 waters react with each other to make hydronium hydroxide, and then as quickly as that's formed, it will go back and shift back the other direction. So it's a very dynamic equilibrium, constant process happening. Okay? Okay, so we're going to be looking at the equilibrium constant of water then. They give water its own equilibrium constant because it reacts with itself. So we call that Kw. And basically we group this, and yes, you just have to get really used to thinking of hydrogen plus as the same thing as hydronium. So either way you want to write that, you can, but basically the hydrogen ion, which is really hydronium concentration times the hydroxide concentration, and that's always going to give you 1 times 10 to the minus 14. But in pure water, since they're both equally existing and ionizing at the same rate, they're going to end up being 1 times 10 to the minus 7 each. Okay, so if we're in pure water, each of those would be 1 times 10 to the minus 7. So, but in an acid or a base situation, you can always figure out the concentration of the other. If you know the concentration of the hydrogen, you can always figure out the concentration of the hydroxide, because it's always going to multiply out to be 1 times 10 to the minus 14. So that's a helpful equation that you can use. Certain situations, if they give you the hydroxide concentration, but you need to find the pH, you can calculate the hydrogen concentration and then do the negative log and be able to figure out the pH. So we're going to get back to all those lovely equations as well. So no matter what it contains, you should be able to figure out either or if you know one of them. And a lot of these reactions too, because it says at 25 degrees Celsius, they're going to be run at that standard condition. Remember, those are considered standard conditions, 298 K, 25 degrees Celsius. So you'll see these kind of values pop up again in the problems, because we're going to be going back and looking at things from standard conditions. So our possible situations here. If the hydrogen equals the hydroxide, what does it tell you about the solution? It's going to tell you that you've got neutral. And neutral means what kind of pH? So the pH here would be right at 7. However, if we had the hydrogen ion being greater than the hydroxide, what is our pH going to be? Less than 7. And if we have hydroxide in greater amounts than the hydrogen, we're going to end up with a pH that is greater than 7. So some pH scale, remembering the pH scale. Now for our review of formulas. pH, the power of hydrogen. Looking at the amount, basically, of that hydrogen in there forming hydronium. And we're going to use the pH equals the negative log of the hydrogen ion equation in order to figure our pH. Now, why we do that is because for every change in one value of pH, you're really changing the concentration by a power of 10. It is a logarithmic scale. You kind of have to think about it in terms of like your math skills and that logarithmic scale. If we adjust the pH by 1, we're really adjusting the concentration by a power of 10. And remember that we're on the lower end of the pH scale here. 7, below 7 here, we're talking about our acid. What would happen to the pH if we diluted 100 milliliters of 0.1 to 1,000? Well, what would decrease by 1? Or increase by 1, sorry. Yes, the pH would increase by 1. So you're thinking in terms of math, which is good. Those of us that can't process that quickly, as you can, some of us might have to actually think about it. Yes. So if I did the negative log of the 0.100, my pH value should be what? What do you get there? 1. The pH should be 1, right? This is our pH. Yes. Our pH is 1. However, if we dilute, right, you could use your dilution equation. You can actually go ahead and do that. So we have 0.100 times our 100. What's our new molarity when we multiply it by the 1,000 and dilute it? What are we going to get here? What's M2 going to be? .01, exactly, or 0.011 if we were going to go with the same number up here in this measured value. However, put that in your calculator for the negative log. And what's your pH now? The pH now ends up being 2, right? So we diluted it 10 times. So that changed our pH value by a numerical value of 1. So that's how that kind of logarithmic scale works. And hopefully everybody's kind of, I know that's going back to some basic math, but not everybody processes as fast and figures that out as quickly. But that's the basic, setup if you had to calculate it from the beginning without being able to visualize the logarithmic scale in your head. So, changing the concentration by a power of 10 will only lose the pH a value of 1. Any questions on that? We good so far? Because I know you just wanted to have some more significant digit rules, right? Everybody wants to learn a new one? Yeah? There's a new significant figure rule for you. Yeah, it's really fun for pH. pH has its own significant figure rule. Did you know that?
It's unnecessary.
It is necessary. Well, I mean, you'll see. It's pretty necessary here. So the number of decimal places in the log is equal to the number of significant figures in the original number. So let's go ahead and see. Let's do a couple of examples to show you what that means. So I'm going to make up a couple here. Say I'll do a couple easier ones, then we'll do regular or just generalized numbers. So if I have a hydrogen concentration of okay, go ahead, do the negative log of that. And what is our pH? That one is 3, although it's not just 3. Okay? So, here, yes, how many significant figures are in that number? 4. So, this number does not count in terms of the sig figs. You have to put 4 decimal places after that. So that would be 4 decimal places after go coincide with the significant figures in the original concentration. Okay? Yes.
If you're at the concentration of 8 plus, how many sig figs do you use to take one?
Oh, so going backwards here, yes. If we were starting with this, right, you knew that you had a pH of 3.000. Does everybody know how to reverse the negative log equation? Right? Does everybody know how to go backwards on that one? So hydrogen concentration equals a 10 to the negative pH. Remember that equation?
Yeah.
So that's how you would plug it. We're going to write this down later. You don't have to do it right now. We're going to go back over all these equations, but that's how you would plug it in. But what I would look, we have 4, right? So I would look here and go, oh, I need to have 4 digits in my concentration. This one does not count, but those 4 would, so I would carry out my zeros until I had 4 total in the concentration. So let's try another example. Say you have, the hydrogen concentration is 3.24 times 10 to the negative 9. What would that pH be in the correct number of significant figures? So here the pH value is going to be what? The 8, right? Then we're going to carry it out 3 more decimal places. So it'd be 4, 8, 9. So these digits right here, those 3 significant digits apply to the decimal places only. Yes.
So this is only after decimal place. So if it was like 84, and it was like the same number, it would be like 20, and you do 3 again, right? If there was like 84 on the left side of the decimal point or something, would you all?
Well, you're not going to have a pH of 84. Because the scale pretty much, yes, we say the scale goes like from 0 to 14. Technically, there are pHs of like 15 and 16, but you're not going to have one as high as 84.
Like a double digit of 15, like 15 point, which is 3 digits.
No, those 2 digits in front of the decimal do not count. Do not count. So yeah, So that's a good question. Let's do one more where that would happen. Let me give you another example. So where we would have hydrogen as 1.29 times 10 to the minus 11. That should work. So this ends up being what? What is our pH value? 10. Now we start working on our sig fig. So if there's 1, 2, 3. So now I'm going to carry it out 3 decimal places. It would be 8, 8, 9. Okay? So once again, this does not count in part of the determining of the sig figs. The beginning part does not count. Are we clear with how to do the pH sig figs? All right. New little wrinkle for you. pH, POH. Oh, we get to talk about POH. Everybody understands. I want to make sure, because this is kind of a math concept. But this P in front here, everybody knows what that means, or this P here means? Well, it means negative log it, basically. So that P in front of something means if you're putting it into an equation, you're going to do the negative log of it. So in order to get pH, we do the negative log of the hydrogen. If we want POH, we would do the negative log of the hydroxide. Because you're going to see pKa, you're going to see, you know, pKw. If there's a P in front of it, you just do that negative log in front of it, and that would give you your answer. That's kind of a math thing that goes with our notation here. Just want to make sure everybody understands that. So if you have a P in front of it, it really means negative log of that. Are we good? All right, so this is kind of a review from last year, and some of the stuff we already identified. pH of 7 is neutral. pH greater than 7 is basic. The higher, the more basic. pH is less than 7, acidic. Lower, more acidic. The POH, now it's looking at it from the hydroxide standpoint, is also neutral at 7. But the higher the POH, the more acidic you are, the lower the POH, the more basic you are. So it's kind of a reverse of the hydrogen scale. But it does kind of make sense if you think about it. If you're right here, this is the hydrogen side. Okay, right here for the, actually I think I put my arrows the wrong way. Okay, so the increasing the hydrogen concentration, like here would be the pH scale, like here is 7. So if you increase the hydrogen concentration, that also means your hydroxide concentration should be lower. If you're increasing the hydroxide concentration, the hydrogen concentration should be lower. Remember, you multiply the two, you should still get that Kw. If you have high hydrogen, you should have low hydroxide. If you have high hydroxide, you should have low amounts of hydrogen. They are, you know, kind of a pair that work together oppositely. And here's a lovely scale, too, of some common household items. So 1 molar sodium hydroxide up here is 14. 1 molar hydrochloric. So this is where you can get negative pH values, by the way. So some of the stuff in the back there, you know, the hydrochloric comes, I think, as 18 molar. So it's really, really concentrated. So like an 18 molar HCl, which is what I have to dilute when I make the different solutions. So I have to put it in the fume hood too because it gives off nasty fumes. So if you negative log that, you end up with negative 1.26. So it is possible to have negative pH values. We just don't usually work in that particular range. And like I said, the opposite is true. If you have a very, very strong base above 1 molar sodium hydroxide, which is pretty dang strong, you can get into the 15, 16 range. You can get above the normal scale. But we kind of don't really do much with things that are out of the scale because they're too concentrated, they're too corrosive, too caustic, too damaging, and nobody wants to, you know, be around those kind of compounds. Now for the fun formulas. A lot of them to recall. So the Kw, hydrogen times hydroxide. The pKw is going to give you the pH plus the pOH, which is basically the same as this. The pKw, like I said, is the negative log of Kw. The pH is the negative log of hydrogen. The pOH is the negative log of hydroxide. And we did just kind of talk about this one. If you need to reverse, start with the pH and go to the hydrogen. It's just 10 to the negative pH value. And you type that in and go backwards to the concentration. Now the hydroxide also works. You can find the negative log of the hydroxide, giving you the pOH. I like this equation. This one's the fastest way to go between pH and pOH, because when you add them up, they equal 14. So when I have to start with an OH and figure out something on the hydrogen side, this is a very quick, easy way of converting over to the hydrogen side if you were given hydroxide. So, but generally, you'll see they're pretty, common. Like negative log of hydrogen is the pH, negative log of hydroxide is the pOH. They kind of follow the same formula type design, so it shouldn't be too much to memorize in terms of, because really these two formulas, these two sets are very similar, and then these two sets are very similar. Basically, this one and this one are the same, virtually the same thing. Okay, and the Kw one, once again, you just have to remember that Kw is the 1.0 times 10 to the minus 14 value, so you can use that formula at any time. Lots of stuff, yes, but not hard, just have to apply. And let's see here. On the formula sheet, let me tell you which ones they actually give you. So on the formula sheet, they do give you this one. They even give you the 1 times 10 to the minus 14. They give you, both of these are on the formula sheet. Yep, that's out of these what they give you here. There are a few other variations which we're going to go and talk about that are also on this formula sheet. Okay? So actually some of you don't have to memorize because it's on the formula sheet and be provided for you. Alright, so let's do a few examples here. This is more of like problems that we would do last year. So I want to calculate the pH where they give me the hydrogen concentration. All I have to do here is do what? Negative log of this value, and I can get my pH. Of course, expressing it in the correct number of significant digits. We definitely want to do that. So what does this one end up being? Although I can look at this one, yes, I suppose, because it's 1, and then we have a negative 4 here, so this one's going to be what? 4.00. Because this has 2 sig, so we keep the 00 here. B is a little bit more tricky. Why is B a little bit more tricky? Because there's an OH involved. So, you can work this a couple different ways with your different formulas. Any suggestions?
Find the pOH and then subtract that from 13.
Yes, you could find the pOH by doing the negative log. This is probably the method I would prefer too. That this is how my brain thinks. I would do the negative log of the 0.040, and I'd get my pOH. And that happens to be 1.0 1.40. 1.40, that's my pOH. Then, there's only 2 here. That's one, only 2 signals there. Then you would do the 14 equals the pH, the pOH. So basically I do 14 minus that. And I'd end up with pH 12.60, keeping those 2, to the right there for the sig fig. Since this is telling me my sig figs, I would keep those there as well for the correct number of sig figs. All right, pH of a solution is 5.85. What is the hydrogen concentration? What is the one we should use here? 10 to the negative pH, right, equals your hydrogen concentration. Everybody know how to plug that in correctly with using their caret button. What do you get? And how many sig figs? 2, so and everything's pretty much concentration. We're working out of molarity, so you can go with the big M. Couple more. Calculate the pOH, though. Do pay attention to what it's asking for and what it's giving to you. So if I'm doing A, I'm not being given the hydroxide there, I'm being given the hydrogen, right? So, any ideas to work this one? Yes.
So, we do negative log of H, right? And then also the log of H of H, and then subtract those and then
Well, there's this way is going to give me my pH, right? And my pH is going to be, and then I can do 14 minus my 4, right? And get 10. That's one way, definitely. But I think what you were thinking also is we could do the 1 times 10 to the minus 14 as the kW. We could put this in here. That's going to be our hydrogen, and then we could find our hydroxide concentration. And then, once you figured that out, which it should, the hydroxide should have ended up being 1 times 10 to the minus 10, and then you would have done negative log of that. So there are various ways to work it, and we would still end up with a pH of 10. So you could do the blue way up here, the first way, or you could have done it the green way, which would be the second option. You're welcome. Whichever way works better for you and faster for you, please use it. B is easier this time, right? Because all we have to do is what? Plug it into the negative log of the hydroxide here will give us our pOH. And what is that going to be? We got that already. That was what? 1.40. This one? Yeah. Well, no, I mean, we're treating it as though it's its own individualized problem, but yes, we're using the same numbers to kind of see the pattern, but yes, I get what you're saying. Sure. All right, pH of a solution is 5.85. What's the hydroxide concentration? Once again, now we're looking kind of the same number, but working it to a different particular one. So what could you do here? Yes. So I would do that too. I would do the 14 minus the 5.85 and get my pOH, right? What do you get for your pOH? 8.15. Then I can just do 10 to the negative 8.15 and get my hydroxide concentration. Does anybody like that pop in your head first to do it that way? You could also, find the hydrogen concentration and use the Kw equation. You could do it that way. This is the fastest way I think of to do it, but like I said, if you think Kw, you can use the Kw one. So this ends up being, we want 2 sig figs, so 7.1 times 10 to the minus 9 molar. Now, thinking about acid-base problems. What are the major species in solution? What is the dominant reaction that will take place? Is it equilibrium reaction, or is it essentially going to go to completion? React all major species until you're left with an equilibrium reaction, and you can solve for pH. So there's a lot of things to consider up here when you're thinking about acid-base problems. We're going to start with basically looking at the first two bullets right now. Okay? Looking at what are the major species in solution and what's the dominant reaction taking place in order to figure out things. Thinking about the acid-base problems, you really do have to take into account that the idea that because water is the major species in the solution, water is going to also be a possible reaction that takes place, that self-ionization of water, in terms of who's donating the most protons and controlling the pH. So you have to always think and look back, and this is a very rare question that's been on the AP exam, but it has shown up, where they'll give you, a very weak concentrated, a very weak amount, weak concentration of a strong acid, but you have to realize that that was not going to be controlling the pH. It's actually going to be the self-ionization of water reaction. So we also, when we're going through these problems, we need to take that into account and have that always in the back of our head, looking for that. Most of the time it's not going to be there. It's a very rare occasion when it does pop up. But we need to be looking for the dominant reaction first. Then we can calculate based off of which one's dominating the pH and the concentrations from there. So here, once again, we're looking for the major species. We do know that this is some stuff we went over last time, that hydrochloric, the strong acid, is supposed to completely dissociate or ionize in water. Okay? Completely dissociate. So you get the, HCl plus the water. It's going to make the hydronium and the chloride. So basically, I draw the arrow in this direction because it's supposed to go to completion. It's not really one that reverses a whole lot. Okay? So we're really looking for the major species that will begin this now has dissociated. It has become hydronium and chloride. It's really no longer around. We still have water though. There's plenty of it in the beaker. And we have hydronium now, and we have chloride now. These are going to be what our major species that we're going to be looking at. In this case, the reason why I know this is if I look at the concentration here, this says 10 to the minus 3. And remember, our pH scale is a relative log, it's a logarithmic scale. So something that is 10 to the minus 3 is going to be somewhere in that 3 to 4 pH range, okay? Something that's 10 to the minus 1 should be like somewhere in the 1 to 2 range, okay? Thinking about that logarithmic scale that we were talking about last time. So I can tell, if I'm looking here, that that's a pretty high concentration, okay? And looking there, that particular case, the hydrochloric acid and its reaction with the water here and creating the hydronium and the chloride is going to be the dominant reaction, and it's going to control the pH. So, as you can see here, highlighting once again the major species because this completely dissociates, and we have a pretty high concentration of it. We know that that would be the dominant reaction there. And our pH, like I said, is going to be in that lower range, and it happens to be 2.7. Now here, once again, this is where, you know, these ones seem, oh, they should be super easy, not a problem. We have nitric here. Nitric's a strong acid. Nitric's going to react with the water. Also going to completion, giving you hydronium and our nitrate as our conjugate over here. So major species. Now I don't really have to consider the self-ionization of water, because if I'm looking here, once again, 10 to the minus 2, that's going to be in the lower part of the pH scale. That's going to be down there, and that's going to be driving the pH. Very, very, you know, more concentrated amounts there, okay, that I should be looking at and considering. Okay? So then, as we did before, we would just take the negative log of that and get our pH. So as you can see, the major species, once again, because this one pretty much goes to completion because it's strong and completely ionizes or dissociates, we end up having that as well. And our pH is 1.82, definitely driving it. And this is where we need to pay attention, though. Still strong acid, this is that last one, strong acid hydrochloric. But if we're looking here, 10 to the minus 11 is a very small amount of hydrochloric being dumped in. The self-ionization of water reaction, and I'm not sure everybody understood this last time, so I want to make sure we go over this. Okay, we'll produce the hydronium and the hydroxide, right? And it has its own constant. It's the Kw. Concentration of the hydronium is going to be multiplied by the concentration of the hydroxide. And if we are, you know, since if this is pure water, okay, going for the pure here, nothing's dissolved in it or anything, then our pH should be 7, right? Everybody understand that pure water, the pH is 7? Okay, so that means that if it's 7, the concentration of the hydronium should be 1 times 10 to the minus 7. The concentration of the hydroxide should also be 1 times 10 to the minus 7, because Kw is always going to be 1 times 10 to the minus 14. So looking here at our concentrations, this is where I want you to pay attention to that self-ionization of water, is that we end up with this 1 times 10 to the minus 7 concentration that is driving this particular formation of the hydronium. And in comparison to our other concentration of the hydrochloric up here, which one's going to have more impact? Which one's the larger number? This one is 1 times 10 to the minus 7 is a larger number than our 10 to the negative 11, right? So as you can see, the concentration of the hydronium caused by the self-ionization of water would be higher than the concentration that would be caused by the hydrochloric up there. So that's why we know this one is the dominant reaction in this case. And when we know that that's the dominant reaction and it's going to be driving the pH, we would take the negative log of this value, the 1 times 10 to the minus 7, to know that the pH should be right at 7. So just adding a tidbit of acid really, in this case, was basically what's going on here, is they're adding just a tidbit of the hydrochloric. It does not drive down the pH. The pH pretty much stays at 7 because the water is so abundant that it's not really affecting it, and the water self-ionization is keeping it at 7. Okay? Just wanted to reiterate that point because that has shown up on an AP exam where they'll give you this very small little amount of a strong acid and ask you for the pH, and you're like, oh, easy, negative log that, and you get this, you know, pH that's like 13 or something. Well, actually, the pH really should have been at 7. So I don't want anybody to lose a point for that. 7. So in this particular case, because we added very little, very, very little amount of HCl, your pH is still virtually 7. Didn't change a whole lot.
I use water and use 1 times 10 to the 7, but not 1 times 10 to the 14.
Well, because the kW is 1 times 10 to the minus 14. If we're using pure water that we're dumping this little bit of HCl in, the virtual concentration of both the hydroxide and the hydronium are at 1 times 10 to the minus 7. They're equal. Because remember, pure water should be neutral, should be 7, right? So the hydrogen should be 7, negative 7, so should the hydroxide be negative 7. That's where I'm kind of getting those numbers from, but that's a good question. Yeah. So the pH of this one would be, dominant reaction happens to be your self-ionization of water going on, and water is the major H donor, so that creates pH of 7. Yes. Yeah, they completely dissociate or they completely ionize. So the arrow pretty much just points in the completion direction, yes. Now, the weak ones obviously only partially dissociate or ionize, and that's why we use the double arrow, and they do have an equilibrium position based on how much they will actually form that. And we say ionize here, and we've been using the word dissociate when it comes to the salts, but technically if you're looking at this, when we move a proton over to the water and create hydronium, we're actually creating ions or ionizing the water. So in this particular unit, the word ionize is more preferred over dissociate. Even though dissociate is still, correct, they are breaking apart, but they are also, the H is attaching to the water, creating a new ion. So there's a little bit there, now it's a little bit of a nuance with the words, but in acid-base, it's more of an ionized word versus dissociate, which is what we were using for ionic compounds and salts. Okay? Ka is known as the acid dissociation constant, but it's basically the equilibrium constant for weak acids. You can use it for the strong ones, but most of the time this is really finding the equilibrium position of how much it's going to ionize in the water. And strong ones typically completely dissociate, so we don't really use Ka a whole lot when we're talking about strong. Is a quantitative measure of the strength of the acid. So things that have very large Kas are going to be stronger. Things that have smaller Kas are going to be very weak. Kind of goes in concept with the KSP idea. If you had a larger KSP, more would dissolve. If you had a lower KSP, you are more insoluble. So kind of try to think about it related to the KSP concept as well. And they like to use the word ionizes a lot in terms of the acid-base stuff, because really when it breaks apart, it's creating those ions. And before we used to just say dissociate when we were talking in Unit 1. Breaking apart, forming ions is also dissociation. So like I said, introducing this new idea of calling it ionization. You'll see that that terminology a lot more frequent in the acid-base chemistry. So it really describes the reaction of how much the acid ionizes in water. So you want to think the Bronsted-Lowry kind of reaction here. So if you're told the Ka for the acid, you know the equilibrium constant for the reaction with water. And you can figure out how much of the hydronium is formed, how much of the conjugate base is formed. Depending on the size of the Ka will be dependent on how much actually ionizes. Small Kas, not very much ionizes. Not very much of it goes over here to the right for the product side of things.
Wait, small Ka means that it's
No, a small Ka means it's very weak, so it hardly ionizes. A large Ka, which very large Ka, would be ones that completely dissociate.
and Ka is used to describe acid weakness.
It uses the strength of the acid. So a smaller Ka value will tell you it's weaker than something that has. So if I have like a Ka that's 10 to the minus 9 and a Ka that's 10 to the minus 3, which one would be stronger? The 10 to the minus 3 one would be stronger. Kb is pretty much the same thing, except for it pertains to bases. And there's not a whole lot of weak bases out there that we want to be looking at, but most of your weak bases are going to have some kind of amine group attached, like that, some kind of amino group. But most of the hydroxide ones are pretty insoluble and don't dissolve a whole lot, besides our alkali metals, which are strong, and then our 3 alkaline earth metals, the heavy ones, calcium, strontium, barium. Those hydroxides are considered strong, and they are in the slightly soluble category. So, but we're looking here, you're going to see this one with things that have amines attached to it, or you'll see, of course, ammonia a lot, because ammonia is considered one of the weak bases. So you'll see ammonia pop up a lot when we're dealing with the weak base equilibrium problems, okay? But it is a measurement of the strength of the base. It's also, about how much of that base is ionizing, creating hydroxide in the solution, okay? So basically showing how much of the base is going to ionize in the water, same idea. But most, for these ones like ammonias, I think in the 10 to the minus 5. So it ionizes some, but there's a lot of the NH3 that just stays there and doesn't react with the water, creating the hydroxide. Okay. Any questions so far? 2 new equilibrium caves to talk about. Following basic equilibrium concept here still, where you're going to be, looking at the ratio of the amount ionized of the products over the original concentration, and then we're going to be able to tell concentrations of the individual species, or you can know the concentrations of the individual species and be able to calculate your Ka or Kb. Kind of the same stuff that we did with equilibrium. A little bit of variation on there, but similar. Now applying it to acids and bases.